This is part one of a two-part thing on simplifying radicals, and the first part that we're going to talk about is radical forms that only involve multiplication, and we'll save the division of radicals for a second presentation. So the idea of a radical, a square root, is the thing that squares to make. So here's the formal definitions and the formal rules, but typically you think of something like the square root of 16 to be a 4. Well, why do you know that the square root of 16 is a 4? Because the square root of 16 is asking, what's the thing that squares to make a 16? And I happen to know that 4 times 4 is 16. So these are the formal definitions of the square root and the rules of simplification. That is, the square root of a product becomes the individual product of the square roots. And this is probably what you remember from sophomore geometry, because quite often when you work the Pythagorean theorem, you end up having to take the square root of a 50, and the square root of 50 is thought of as the square root 25 times the square root 2, and the square root of 25 I know to be a 5, but the square root of 2, I don't know. I could make a decimal approximation, but it would only be an approximation. That's why mathematicians leave it in this form. So when I deal with radical products, the first thing I always do is to list all the numbers whose square roots I know. So I just say 2 times 2 is 4, write the 4. 3 times 3 is 9, write the 9. 4 times 4 is 16. So all these numbers are numbers that I could tell the square root for. For instance, the square root of 49 is the thing that squares to make a 49. I know that's a 7. So on things like this, I always break it down in the following way. A square root times a square root, and the first square root is the biggest number in the list of perfect squares that goes into the radicand, the thing in the radical. So that would simply be a square root 4 times a square root 5. Square root of 4 I know to be a 2. Square root of 5, it's the thing that squares to make 5. It's about a 2.23, but that's simply an approximation. That's why this is considered correct. Now I could think of 9 times 8 for 72, but the 8 would have to be broken down later in a second step. And so I always think of the biggest possible number in the perfect squares list that can go into my radicand. That would be a 36. 36 times 2 is 72. So the square root of 36 I know to be a 6. The square root of 2 I know is the number that squares to make 2. It's about a 1.414 is a decimal approximation, but again, that's just an approximation. Square root of 80 I could think is 4 times 20, but the 20 could be broken down in a second step. So instead of taking multiple steps, scan the list, and the biggest thing that goes into 80 is a 16. So the square root of 16 times the square root of 5 makes the 80. The square root of 16 I know to be a 4, 4 square root 5. All of these can be simplified on a TI Inspire calculator, but it's quicker if you know your multiplication facts to do it this way than it would be to type it in on a calculator. By the way, that's one of the things that kids that don't learn their multiplication facts always struggle in algebra, because they don't recognize simple relationships like that. All right, so this is the next jump up, and I see this as 3 things multiplied. So I leave the 5 as one of the factors, and there's understood multiplication right there, but I break down the radical the way I just did in the previous examples. So this then becomes 5 times 4 times the square root of 2. I know 5 times 4 to be a 20, so I simply call that 20 times the square root of 2. 3 times the square root of 12 would simply be 3 times the square root of 12 is the square root of 4 times the square root of 3. Square root of 4 I know to be a 2, so this simply becomes 3 times 2 times square root of 3, or 6 times square root of 3. Please notice that in multiplication, I can't do all 3 numbers at once. And if I give you a simple problem like 5 times 2 times 17, you see instantly that that's a 170, but do you realize that you can't do the whole thing in one step? You realize that 5 times 2 was a 10 in the first step, and then that product was multiplied by the second factor of the 17 as a second step. And that's how I got the 170. I'm doing exactly the same thing here. I can't multiply 3 things together, so the 2 by 3 makes a 6, and it has to multiply the remaining number. Where I know 10 times 17 is 170, the best I can say about 6 times the square root of 3 is that it's 6 times the square root of 3. Now, because I'm a whiz at multiplication and because I know my doubling series, because it's a pretty common thing to bump into in computers or in math, I happen to recognize that 64 times 2 makes 128. 64 is the biggest number in my squares list that goes into 128. So this simply becomes 8 times 8 times square root of 2. Same principle as above. That becomes 64 times square root 2. The next step is when I have several problems of that same ilk. And so I rearrange my factors. I don't have to write it this way. I just have to imagine it this way. And so it becomes 4 things multiplied to look like this. And then I can tell you the answer of the 2 times 5 is a 10. I can tell you the answer of the square root of 20 times the square root of 10 is a square root 200. But that would require that I break it down a little bit further. I would call that 10 times the square root of 100 times the square root of a 2. And then square root of 100 is known to be a 10. 10 times 10 is 100 times the square root of 2. I want to show you another way that I could have approached this. And it's a really good technique when you recognize that it can be done. Notice the answer that I had just a second ago was 100 times the square root of 2. So I'm just going to write that over there just to remember that's what the result I had by the traditional technique. Because a square root of 10 is the thing that multiplies itself to make a 10, I recognize that the square root of 20 could be re-expressed as square root of 2 times square root of 10. So that's not the customary way to simplify the square root of 20. But because I saw this square root of 10 needs another square root of 10 to create a 10, that's what I'm doing. So that this becomes 10 times 10 is 100. There's my same 100 square root of 2. So if I were doing this problem, I would think of it as a negative 4 times a 2 times a square root of 32. Whoops, let me break that down. As a square root of 16 times the square root of 2. And then I'm going to go ahead and break down the square root of 10 in a non-standard way. I'm going to call it the square root of 2 times the square root of 5. And the reason I broke that down is that I recognize that the square root of 2 that came out of the square root of 32 needs another square root of 2 if it could find one to become a nice 2. And there's a square root of 2 as part of the square root of 10. So now I would have a negative 8 from the whole numbers times a 4 from the square root of 16 times a 2 from this pair of square roots multiplying times a square root 5. So this would simply be 8 times 8 negative, so negative 64 square root 5. A lot of these things where I rewrite, I could do in my head. For instance, I could just look at this and say there's going to be that negative 8 right there. And sometimes I might even write directly above square root 16, square root 2, square root 2, square root 5, as opposed to writing it out to the side. The next little step up is when I see things that look like simple parenthesis expansions that you've seen before on things like 2 times x minus 5. So the 2 simply multiplies both parts of the paren. That's what happens here. The 6 multiplies both parts of the paren. I see this as a 2-termed expression in my paren with a single thing on the outside that's going to multiply both parts on the inside. It's exactly like a distributive rule expansion that you would use like this. So this then becomes 2 times the square root of 12 plus 5 times the square root of 6. And then the square root of 12 would simply become 2 square root 3. And then 2 times 2 square root 3 becomes 4 square root 3 plus 5 square root 6. Those are unlike terms. If I was adding square roots of 3 to other square roots of 3, it would create more square roots of 3, but these are unlike. It's like x is added to y's. You can add them, you just can't crunch it into a single answer. Same thing down here, just watch the signs. Negative times positive is negative, 4 times 7 is 28, and then the square root of 15 is part of the package that's coming into the parenthesis as a multiplier. The second term will be a plus, so I'll have negative times negative, 4 times 3, 12. 150 times 10, sorry, 15 times 10 is 150, so the square root of 150. As such, the square root of 150 could be thought of as the square root of 25 times the square root of 6. Then 5 square root of 6 would become the eventual simplification of this, but times it by 12, so that this eventually becomes 60 times the square root of 6. And then over here, there's no simplification on the negative 28 square root 15. And so that's considered to be the simplest form of that. You don't often bump into these things that complicated, but you'll often see a radical coming into a parenthesis, and you just treat it like you learned in Algebra 1 for a set repetition. So next, these are the types of problems that are the most common, believe it or not, as you press on into the deeper topics of Algebra 2. They are FOIL multiplications for radical expressions, and so I just use simple FOIL. I say first times first is first, that's a 2. Outside pair, sign number power, the sign is negative, the number is 1, and there's a square root of 3 in that. Inside pair, sign number power, it's a positive, it's a 2 times the square root of 3. And then last times last, sign, negative, the number would be 1, and then the power is like saying square root of 3 times square root of 3 is 3. Now notice here that I get real numbers, or excuse me, not real numbers, rational numbers in the first and last that need to be combined. On any other day, if you saw 2 subtract 3, you'd call that a negative 1. We should do so here. This time I do have like terms here. Square roots of 3 added to square roots of 3 make more square roots of 3. How many square roots of 3 are there? Positive 1. So I would simply list that as negative 1 plus square root of 3. FOIL problem down here. First times first is 14. Outside pair, sign is negative, number is 6, and the square root is a 5. Inside pair, sign is negative, number is 28, and it's a square root of 5. Last times last, sign is positive, number is 12, and the square root 5 times the square root 5 is a whole number 5. Again, notice the first and last terms will be nice rational numbers. 12 times 5 is 60, positive. 14 plus 60 is 74. And the inside terms are also like terms. Square roots of 5 added to square roots of 5 are more square roots of 5. In this case, negative 34 square roots of 5. This is another FOIL, but please notice this one. This is a rather unique FOIL multiplication because the two terms are identical except one is plus and one is minus. This pair, as a pair, are called conjugates. And conjugates always look identical to each other except they differ by a single sign. Most often it's the sign in between the two, although the sign can be the first term. So what that means is it's a waste of time to look for the middle term. All I should do is first times first, 16, last times last, sign negative, number 3. If I look for the inside-outside terms, I would have a positive 4 square root 3 on the outsides and a negative 4 square root 3 on the insides, which would equal a 0. So it was a waste of time to even look because the identical numbers with the plus-minus pattern will always cause the outside-inside to equal 0. I should go ahead and call this 13. This is so common and it's going to show up in so many problems. Get used to it. This one here I could do as a FOIL, but I'm not. I'm going to do the binomial expansion. First term squared, twice the product, second term squared. The second term squared is a plus 3. And again, notice the first and last are rational numbers, so that's a 7 minus 4 square root 3. So I handle all of these things just like I've handled things in the past, like x plus 3 times x minus 2. That's just a simple FOIL multiplication. Or x plus 2 times x minus 2. Don't look for the middle term on that one. There won't be one. And I'd simply call that an x squared minus 4. Or if I had x plus 5 quantity squared, I'd say first term squared twice a product, second term squared. Same exact principles with radical arithmetic. So that's the end of multiplication with radicals. Next video is about division with radicals.